Hello everyone, Aaron here and welcome back to Leetcode. Today we're doing the longest path with different adjacent characters problem. First, a couple of admin notes. I know it's echoey. I have just moved into a new flat and I'm still getting furnishing sorted. It's going to be like that for a while. Two, there may be some technical difficulties during this video because there's been problems getting broadband connected and I'm doing this via a hotspot. It might also take me 1,000 years to upload. We'll find out. So for the next couple of weeks, if videos are a bit all over the place, it's probably because one of those two things is, basically the internet will be dead or the echo will be so bad you can't hear a damn thing I'm saying. Right. Now, getting into the problem. You were given a tree, i.e. a connected undirected graph that has no cycles. We saw one of those a couple of days ago. I think the last video I did. It's rooted at node 0. So this is a bit of a difference. The last one I don't think was rooted. It has n nodes numbered from 0 to n-1. So 0 is our root. The tree is represented by a 0-indexed array, parent of size n, where parent I is the parent node of I. Okay, that makes sense. So 3 has a parent of 1. For example, and 4 has a parent of 1. So they can only have one parent. Since 0 is the root, parent 0 is -1. That makes sense. You are given a string s of length n, where si is the character assigned to node I. Okay, that's all straightforward enough so far. So here this will be given as ABA. Return the length of the longest path in the tree such that no pair of adjacent nodes on the path have the same character assigned to them. Okay. Return the longest path. So here we can do A, B, C. We basically can never cross this bridge because both of its nodes have the same label. And we can never cross this bridge because both its nodes have the same label. But everything else is fair game. This one here. We can't cross this bridge, but we can cross both of these bridges. So there are 3 nodes along that path. And that's it. I immediately want to do something a little bit like a Kruskal's algorithm for minimum spanning trees. So I basically want to work out what clusters of nodes can connect to one another, and then probably just find the longest path between those nodes. So for example, here we would break this into 2, 5, 0, 1, 3, and 4, and we would see that the longest path is those 3 there. Here we would cut the 1 off and be left with those 3 there. The problem with this approach is it doesn't quite give us paths, it gives us trees. But there's probably a way to convert a tree into a longest path relatively easily. So how do I want to do this? Let's do the valid neighbors. I'm going to make this a default dict of a list. This is a hard problem, so I'm not going to do a lot of the absolute basics to talk through here. If you're tackling this one at all, you're smarter than I am. Right, so in fact, let's do this as a function, self.collect edges parent. I'm going to leave, in fact, I'm also going to need to send s with that as well. Once I've got the valid neighbors, self dot, let's call this regions is how do I want to do this actually? Maybe I don't want to divide it into regions. Once I've got all the valid edges, all I need to do is, well, what we want to do is we want to find the tips. So if I can, so once we've cut this into 2 and 5, 0, 1, 3, and 4, I want to be told 2, 5, 0, 3, and 4, for example. Those are the tips I want to learn about. And then what I want to do is basically for each tip, I want to go as far as I can. Because I know the longest path I can take from any of those tips is the longest path, because I'm only collecting the valid neighbors. Paths can be an empty list for tip in self.tips. Paths.append self.find longest path tip. Turn max paths. There'll be some optimizations we might have to do here, such as this region only has 2 nodes. We'll see. The way I'm going to find the tips, by the way, is, well, we'll get to that. First, let's deal with the easy one. Collect edges. Self, parent, s. So basically, I need to neighbors is going to be collection of default dict with a list, except there's no underscore in default dict, for I in range 1 len parent. What I want to do is effectively, well, this parent relation gives me everything I need to know. I want the neighbors of I append parent I. In fact, I'm going to make this a set. And then it's neighbors of the parent of I, add I. But this is only doable if si does not equal s parent I. They must have a different label. Label, character. Yeah, they must have a different character associated with each other. what I'm going to do is I'm just stub out the rest. Def find keyboard in the wrong place. Def find edges of regions. Self, that's going to pass. Def find longest path. Tip self. Start. So let's just see what we've got so far. I don't. Okay, so it did show me at least this thing. So from 1, you can get to 0 and 3. That's correct, but you can't get to 4, which is good news for us. From 0, you can get to 1, but you can't get to 2. From 3, you can get to 1, and that's it. From 5, you can get to 2, and that's it. And from 2, you can get to 5, and that's it. See, what I might do initially is just do I set for I in range len parent. So what that'll do is it'll give me a slightly different dictionary. Now 0 connects to 1, that's correct. 1 connects to 0 and 3, that's correct. 2 connects to 5. 3 connects to 1, 4 doesn't connect to anything else, and 5 connects to 2. So that kind of does what we want. We've basically kept only the edges that are relevant. So here for node in node neighbors in self.valid neighbors, tips can be a set to begin with. Return tips. If len neighbors is precisely equal to 1, in fact less than or equal to 1, tips.add node. So this will tell us 0 is a tip, 1 is not a tip, 2 is a tip, 3 is a tip, 4 is a tip, and 5 is a tip. Let's check that is true. Oops, self.valid neighbors items. Okay, that's fine, that's a different error. So it's told us 0, 2, 3, 4, and 5 are the tips. The one question is, why don't I just pick one tip from each region, I suppose? And that would be because if I have a tree, for example, the tip I might pick might be bad tip. It might be sort of sitting somewhere near the middle of this long chain style tree. And then it would only sort of be able to get halfway on its diameter. And we can't really know in advance whether that's right or wrong. So we just have to have to take all the tips. Right, so find longest path. This is basically just give me a depth first search. So let's go with scene set stack is a list while, and we're going to put start in there while stack. In fact, what I'm going to do is I'm going to do the start. Actually, how do I want to do this? Let's just record the whole path. We can trim this later. Path is stack.pop. If When do I want to stop? If I want to stop when there's no neighbors that I haven't seen. If all self.valid neighbors of the end of this hang on, n scene for n, sorry, I just completely froze for a second there. If every neighbor has been seen for this current path, max path is equal to float, in fact, let's just call it 0. Max path is the max of max path and the length of that path. Else path, in fact, scene dot add path -1. Oops, indexed at -1. So I've seen the end of this path now. In fact, I need to check that. If path -1 in scene, continue. Otherwise, what I want to do is add the end of the path into the scene set for neighbor in self.valid neighbors of the end of this path. I want to stack.push path plus neighbor return max path. So here, for example, if we're at 2, what we're going to do is we're going to first check, have I seen all the neighbors? 1 is the only neighbor. I haven't seen 1, so we're in this case. I'm going to mark 0 as seen. I'm going to continue. The neighbor is 1, so I'm going to push 0, 1 onto my stack. I'm going to take 0, 1 off my stack. It can grow down to the 3. 3, the only neighbor that's left is a, hang on, if neighbor not in the scene. Let's just do that little optimization now. Okay, this at least should get all the way through. Oops, not push, append. Although push is the correct term for a stack, in Python it's append because we're modeling it with a list. Okay, this works. Oops, I don't need to be printing. Question quickly becomes, is it efficient enough? The worry is we need to do this search for every tip. And this search could be very expensive. I'm just trying to think whether there's a way of knowing a priori how many nodes are going to be on this path, because I'm worried I'm going to end up with a tree here with 1, 2, 3, 4 nodes whose longest path is 3. I don't know. Let's submit it and see what cases we hit. No, it's definitely not fast enough. So the question becomes, how can I speed it up? That's one big long chain. That's all that case is. It's one big chain. But the problem is it alternates RZ, 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 RZ. So we know a priori here that we're never going to have a very big chain. More precisely, if rather than find edges of region, I found the regions. That just feels horribly wasteful, though. What do we want to do? What do we want to do? What do we want to do? Okay, let's say we have our valid neighbor set. I'm at 0. I want to follow that valid neighbor. A valid neighbor. Hang on. What I want to do is max path if len max path is greater than len path else path. So what this will do now is return a path rather than just a number. So for every tip now, effectively I can cut the amount of work done in half, but this doesn't feel like a big enough fix. Self.find longest path going through the tip. 4p in path, self.scene on. That doesn't need a self on it. I'm not using it anywhere else. Don't add p. Paths.append. In fact, we no longer need to do this in 2 goes. Max path is equal to 0. Max path is the max of max path len path. If tip not in scene on path, in fact that works more generally. If I've, no, it doesn't work quite. No, it does work generally. If I started at 1, I could explore to the 3 or I could explore to the 1. Either way, the length of the path is going to be 2. The trick is, for one of those tips, I'm not going to I'm not going to have reached it already, so that's okay. So I don't think I need to do this for tip in range len parent. I think is fine. It might mean we're starting in a few more places than strictly necessary, but we're going to be just searching a whole lot less space. How can I copy this? To be a test case. Is there an easy way to do that? Leetcode, if you're listening, it would be really nice to have a way to turn a failed test into a test case rather than having to copy, paste, and hope, and then go back and hope. Particularly for these speed problems. Like, I'm not learning anything here. Oops. Max path, we changed that. Time limit exceeded. Okay, let's rethink this. If I've managed to find that, well, no, this one's easy. I can start there and just keep walking until I get somewhere. Every branch I don't take, I can just add to an explore later thing. The trick becomes when it's something like this. I can go there, or I can go there, or I can explore that later, but I need to be able to join those. And I can't do this super recursively, if that makes sense. My options are either take two of the children, or take one of the children and the parent path. So if I'm here, my options are to extend this way or to extend this way. Is that how we do it? So here, for example, I could take both of those. Take the path connecting this way. Well, I couldn't because it's got an A. Or I could take a path that goes down this way. But that would... Okay. What if for every node I calculate its downward chains for both children? So here, 0, 0, 0, 0, 0, 0. This is a... this is a 1, 0 node. This is a 1, 0 node as well, actually. So then this one here is going to be a 0. And then I can do this one, so it's going to be 1 plus the longest of these. Let's try something like that and see if we can get somewhere with that. So I don't actually want to do any of this now. I need to find the leaves, effectively. Def find leaves self parent. What I want is I want to find, what I want basically is set range len parent minus set parent. So let's first start there. Print leaves. That probably doesn't need to be a self. Okay. Three, 4, and 5. Good. We've found the leaves. Now they've got the leaves. Paths down is going to be none times len parent for L in leaves, paths down, L is equal to 0, 0. And then what I want to do is do the Q is collections.Q deck starting with the leaves. In fact, no, I want to do it with set parent P for P in leaves. So I want to start with the 1 and the 2 here. Let's print down the paths down and the Q. Oh, but I need to know the children as well, don't I? Because I need to know what this is reading from. Successfully filled in those. Successfully on 1 and 2. So doing something right. So the children is going to be self.valid children parent s. Def valid children self parent s. So as before, my thinking is let's not include the children that have the same letter. Let's just call that a bad connection, and go from there. So children is collections default dict with sets for I in range 1 len parent children hang on, if s I does not equal s parent I, the children of the parent of I has I in that set. So let's just check we're also building children correctly. Zero has children 1, 1 has children 3, 2 has children 5. That's correct because we're ignoring those two connections. Good. Now, for node in, no, while q. Node is q.pop left. What I want to do is I want to say, for example, this one here, for child in children of the node. Actually, I don't know how many children it's got, do I? So let's just make this an empty list. So for each child, path is going to be an empty list. Path.append 1 plus max paths down of that child. So for example, here we know one of its children is this E. With a default of 0. So this one has nothing, nothing below it. So it's going to just be 0. I certainly hope that works. So this is going to be 1. It's going to be just a list with 1 on it. Here, this is also going to be a list with just 1 on it. Up here, we so then what I want to do is I want to do q.append parent of the node. Once I've processed 2, I want to be able to process this guy, but first I need to process this one, which is fine because we will have already handled it with that leaf. We're working up in layers effectively. Now, actually, is it possible that I can work out of order here if I have different depths and I start at the wrong depth? I think that might be possible to try and process something early. If children of node is none, q and node continue. We'll process it later. We'll have to come back to it. For now, that's a bit of a hacky solution. So print paths down again. Let's see where we're at. None type object is not iterable. Oh, it's yeah. If any of the paths down of the children that's when we want to bail. What do I actually want to do with paths here? I need to do something with paths. After I've done that, what I want to do is I want to do paths down of node is paths. turn off the big test case without deleting it? I don't know. I don't have much choice. I just need to see what's happening here. It may still be timing out because I've got an infinite loop somewhere. Yeah, time limit exceeded. Let's print the queue. And see how far we get. Oh, but it won't show me the print as I go because it needs to finish, and then it'll tell me time limit exceeded. Ah, poop. Oh, no, it is showing me. 1, 2, 2, 0. Hang on. Parent node is not -1. One and 2 go in, 2 and 0 go in. Oh. I need to manage the scene set. If node in scene, continue, scene.add node. Oops, that should be a does not equal. So the number of nodes below the 0, none, hang on, what is that complaining about? Oh, no, the return type is bad. That's fine. So here this is telling us below this one, the longest path is of length 2. It has 2 nodes in it. That's correct. This one here, for below node 1, the longest path is 1. Yeah, that's fine. Here, the longest node is 1. That's correct. Okay. So now what we need to do is go through paths down. And our options are max path can be 0. For path in paths down, for paths in paths down, if len paths is equal to 0, continue. len path is equal to 1, max path is the max of max path, paths 0 plus 1, because it's the number of nodes below it plus 1. Else, what we want to do is basically we want the top 2 values in this. Paths.sorts paths -1 plus paths -2 plus 1. Max path is max path best. Now the reason best is defined as paths -1 plus paths -2 plus 1 is effectively this case here. This one has a 1 path, this one has a 1 path, this one has 0. So let's just take those two and glue them together. That seems like the best way to do it. So that's 1 plus 1 plus the node I'm passing through. Return max path. And I guess the question then is what happens if there's a break? No, I think that's handled here. Okay, that seems to work. Whether it's any better, I don't know in terms of speed. I had to get rid of the big case. We'll probably hit it again now. Wrong answer. Oops, I don't need to be printing. Why did this one go wrong? Well, let's just special case it. If len parent is equal to 1, return 1. Oops. Let's just quickly add a case. It was this -1 with a z on it, or z, however you want to say it. We're handling that now. This is a hard one. Now what? 0 expected 1. Oh. I see, because one option is always just to be yourself. So I guess we could always say that the max path, if I don't have that case anymore, let's add a case here with -1, 0, but they're both mm. Okay, that's handled now. It's sort of this degenerate case here. As soon as there's actually things to connect, we're fine. Oh my goodness, we did it. Oh, I hate these hard ones. They are, well, they live up to their name. They're hard. How long were we going? Nearly an hour. Okay. This was a, bloody hell, this was a hard one. We went down the wrong way to begin with. What did we try? We tried to... Oh, we tried to group the tree and then find the diameter of the subgraphs as a result. But instead, the way to do it was to build up from the leaves and say what's the longest path building from this leaf, and then recursively do that. And that makes sense in a way. It's reusing a lot of the knowledge that we've done, whereas when we were doing the diameter thing, we couldn't reuse a lot of the knowledge, or at least I didn't code it in such a way that we reused a lot of the knowledge. Wow, I hope this video audio isn't too awful, because I think this is a really cool video. Do let me know in the comments how you did it. Is this the way that you attempted it? Did you attempt it at all? It is a hard one. Anyway, that's it from me. Do remember to like, comment, subscribe, all of that good stuff, and I will see you next time. Bye.